So we're talking about functions, and in the first lesson of this unit, we made sketches of graphs that generally related one variable to another, but very specifically, we're going to kind of start to formalize it now, and very specifically, we're going to be talking about one variable being the independent variable, and the other one is the dependent variable, or it changes dependent on this one, okay? So independent variables we call inputs. It's the kind of number, let's say, in an equation that we put in, and then the output is what results. And you're going to see some examples in a moment of what the inputs are and the outputs are, okay? But the value of one variable is uniquely determined by the value of another. And in a couple of slides, you're going to see what we mean about uniquely determined. But you can represent these relationships with tables, listing out the input values and the resulting output values. You can write out in words what's happening. You can write equations for it. We can have ordered pairs, which is like an input comma output, x comma y, and then we could graph those points into some kind of graphic looking figure. Okay, we're going to do all this in just a moment. Now, here is an example they want us to use, representing a geometric relationship. Okay, so you've got a rectangle here, 2 rectangles, 3 rectangles, 4 rectangles, and we're going to be talking about the perimeter, which is the distance around the outside. So in the diagram below, what is the relationship between the number of rectangles and the perimeter, just the outside, not these middle spots, right, but just the outside distance. The number of rectangles and the perimeter of the figure that they form. Represent this relationship using table, words, equation, and a graph. Okay, so this one rectangle, if we went all the way around, what we would have to do is we would have to go 1, and then 6, and then 1, and then 6 again, right? 1, 6, 1, 6, add them all together. Here, we'd have to go 2, and 6, and 2, and 6. Here we'd have to go, with 3 rectangles, you'd have to go 3 units this way, and then 6, 3, and 6. Here we'd have to go 4, and 6, 4, and 6 to get your perimeter all the way around, okay? Now, interestingly, when we're talking about independent and dependent variables, which variable is the dependent variable? Well, the perimeter depends on how many rectangles we've got sitting together, okay? So the perimeter is the dependent variable. It depends on how many rectangles we've got, okay? So first step, and I'm sorry, it's kind of small. First step, make a table, okay? And we can say, here's the number of rectangles that we've got. Here's the perimeter. We're going to do 2 times the width, 2 times 1 in this case, and then 2 times the length. And notice that the length of these is always 6. 6 going down and 6 going back up around the outside, right? Now going this way is 1 and 1. Here it's 2 and 2. Here it's 3 and 3. Here it's 4 and 4, okay? But the 6 down and the 6 up is always the same, so this is always the same here, okay? So you've got 2 times the width plus 2 times the height or the length, and what is that total? 14. So if we were going to graph this on a coordinate grid, we would say, okay, if the x coordinate, the independent variable, was the number of rectangles, and then the y would be the perimeter, 1 rectangle would have a perimeter of 14, 2 would have a perimeter of 16, 3 would have a perimeter of 18, and 4 rectangles would have a perimeter of 20 when laid out like that. So what? Okay, well, how do we say it in words? So you look for a pattern, and you can describe it in words. So you would say, okay, we would multiply the number of rectangles in each figure by 2, because that's what you get on the width. 1 rectangle gives you a width of 1, and you double it. 2 rectangles gives you a width of 2, and you double it. 3 rectangles give you a width of 3, and you double it. So you could say multiply the number of rectangles by 2 to get the total length of the top and bottom sides of that combined figure. Then add 2 times 6, or 12, for the total length of the left and right sides, because that's always the same, so you're always going to add 12 of the combined figure, okay? So this is going to be a constant amount that you get 12 from the sides, 12 from the sides, no matter how many rectangles there are, okay? So then we can use a table, and in the table, we've got, okay, 1 comma 14, so we go over to 1 and go up to 14. 2 comma 16, we go over to 2 up to 16. 3 comma 18, etc. And you would plot it, and you can see it's like a linear function there, right? And somewhere I had the equation, but I don't know where it is, so I'm going to write it down for you, which is essentially y, which is the total perimeter, is going to be equal to 2 times however many triangles there are, or rectangles there are, and since we represent rectangles with x, we would say 2 times whatever x is, the number of rectangles, and then we add on to that the 12, remember, that you get from the up and down, the left and the right side. So 2x plus 12. And if you were to test that out, you could say, okay, well, what if you put in 4 into that equation? 2 times 4 is 8, plus 12 is 20, and there it is. 4 produces 20 out. So now it's your turn. Give it a shot. What you're going to do here is it says in the diagram below, what is the number of what is the relationship between the number of triangles, one triangle, and the perimeter of each that they form. It's got sides of 3 and a base of 4. Okay, represent this using a table, words, equation, and a graph. And you should write those out, and you can refer back to the earlier slide if it helps. Okay, and what if you know that the perimeter, what if there's n triangles? Here's 1, here's 2, here's 3, here's 4. But what if you didn't know exactly how many? What if you wanted to calculate it for any number of triangles that were laid out like this? What would the perimeter be if you had n as the number of triangles? And so now you've got a variable number. Okay. Also then, what would you do to find the perimeter of n plus 1 triangles? Okay. And then here it says, how does your answer in part B relate to the equation that you wrote up here? Okay, give it a go. All right, now something that I referred to earlier, which is the unique output for any one input, is what this is getting at right here. So you can describe the relationship in problem 1 by saying that the perimeter is a function of the number of rectangles. It's a function of, or it's a result of the number of rectangles. Okay, so a function is a relationship that pairs some input value, each input value with exactly one output. I'm going to give you an example of that in a minute. Okay, now you've seen that one way to represent a function is with a graph, and a linear function is a function whose graph is a non-vertical line or part of a non-vertical line, and the change that you get is the same each time. But the big important thing that I want to talk about right here is the idea of a function, okay? The function has some input value. You put it into this machine, and it goes ka-chunk, 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 and it calculates out what is going to come out. And every time, if you put the same thing in, you're going to get the same thing out. It's going to, any input is going to result in just exactly one output. And here is my example for this, okay? You have a Coke machine. And here's the idea. You've got some button. This button is the input. You push that button, right? You put that value in, and it should always produce what? It should always produce a bottle of Coca-Cola. Exactly the same output every time. Yep. This button should always produce a Sprite. You push that button, what should always come out? A Sprite. And of course, this button can also produce a Coca-Cola. That's fine. It's a different input, so it doesn't have it's not a problem. But that new different input, it always results in the same thing, which is a Coca-Cola. Okay. The problem would be if you pushed a button and sometimes you got a Coca-Cola, sometimes you got a Sprite, sometimes you got a root beer, who knows what you're going to get? That's a problem. That machine is not functioning if it's not producing the thing that's on the label. And I want you to keep this example in mind. It's really going to be helpful because I picked this example because you can see that two different buttons can both give you a Coke. That's not a problem. The problem is if you push this button and you don't know whether you're going to get a Coke from that button or something else. You need to be able to guarantee that that input is going to result in the output that you expect, or just one output. So here's my mathematical relationship for that. Y equals x squared plus 1. Okay. If y is the result of putting something in, you could put in, let's say, a -3. And -3 times -3, negative times negative is positive, is a positive 9 plus 1 equals 10. So y equals 10 when you put in negative 3. Well, what if instead of putting in negative 3, you put in a positive 3? Okay, well, positive 3 squared also gives you a 9, right? And 9 plus 1 still also equals 10. They both will result in a 10. 3 and negative 3 both result in a 10. Not a problem. The problem would be, and you can imagine how much of a problem this would be, is if I gave you an equation, and when you calculated it, you got one number, and when I calculated it, I got a different number. That's a problem, right? Imagine taking the test, and you put in the correct number into the equation, but you get a different answer than what I'm expecting. Problem, right? Yeah, because that's not a function. And now two different numbers can produce the same thing, not an issue. It's if one number was giving one person an answer and another person a different answer, that's when it would be a problem. Okay, so this is the big idea with functions, and you really need to get your mind around it. That's why I spent so much time in this slide talking about it. So let's give it a go with this problem. The table shows the relationship between the number of photos x that you take and the amount of memory left on your camera's memory chip. So every time you take a picture, you use some of the memory space up, and so you got less available space as a result, right? Okay. Is the relationship a linear function? Well, let's take a look. If this goes up by 1 every time, does this go, in this case, down by the same amount every time? And it does. It goes down by 3 megabytes every single time. So it is a linear relationship. Okay, now you're going to describe it using words, an equation, and a graph. Okay, here's what it says. How can you tell whether it's a function? Is for each number, do you get a different? Well, first of all, if you have a different number each time, then it's not a problem. Okay, each input is paired with exactly one output. Okay, you're not getting, for any one number, you're not getting two different numbers out. Okay, so no problem. Now, the amount of memory, this is in words, the amount of memory left is uniquely determined by the number of photos you take. You can see this in the table above, where each input value of x corresponds to exactly one output of y. So y is a function of x. Y, the resulting amount, is a function of, it's dependent on x. To describe the relationship, look at how y changes for each change in x. Okay. There's 512 at the start, and this is increasing by 1 each time, and what's happening here is it's decreasing by 3 megabytes each time. Okay, so in words, you would say the amount of memory left on the chip is 512 minus the quantity 3 times however many photos were taken. Okay, so that looks like this. Y, the amount of space left, is equal to 512 minus 3 times the number of photographs taken. Okay, and a graph, you can use the table to make a graph, 0, 512, 1, 509, etc. And here is that table going down like this. Okay, you see this little zigzaggy part? That means that they left out from 500 down to 0 because they were just showing this high part of the graph, and they didn't want to have to graph all the way up from 0 to 500 before they started showing their data. This shows that there's a missing chunk, and you should always make note of that. Okay. So here's your got it problem. Is the relationship in the table below a linear function? Describe the relationship using words, an equation, and a graph. And does this set of ordered pairs, this is fun, represent a linear function? Explain. Give it a shot. Okay, let's see how well you understood that by trying these lesson check problems. Give them a go. You should really test it and see whether you understand what's going on. Good luck.